Welcome to module 13. In this module, we'll go through the non-mandatory steps of life cycle impact assessment and then the final step of life cycle assessment, which is the interpretations. So, there are two optional steps in life cycle impact assessment: normalization and weighting. I'll not talk about grouping and data quality analysis. And in this module, we'll talk about what normalization is and what weighting is. ISO standards do not mandate using the optional steps, but it is sometimes useful, as we will see in decision making. So, what is normalization in life cycle impact assessment? Normalization is the step where we take the relative value of our impact categories with some reference value. For example, this table shows us the impact assessment for three impact categories: climate change, ozone layer depletion and eutrophication, for our LCA, for which we have calculated the flows for 1 kg of product. You can see that our elementary flow is 1 kg CO2 and the climate change value with the characterization factor is 1. So, you have our result is 1 kg CO2 equivalent. We have 10 grams of methane. So, when you convert it into kg, that will be 10 by 1000, and when you multiply it by 25, you have 0.25 kg CO2 equivalent of climate change due to the methane, and similarly for the CFC. So, when you calculate the total impact category result for this LCA, we have 3.65 kg CO2 equivalent of climate change, 7 to the power 10 to the minus 5 kg CFC, 11 equivalent for ozone layer depletion, and about 2.80 10 to the power minus 3 kg phosphorus equivalent for eutrophication. And I hope you remember that these units are coming from the characterization models that we have covered earlier. So, what we do is we are also using the normalization value, which is the reference value. So, here we are using 1.12 10 to the power 4 kg CO2 per year, and the normalization value used here is average for a person in Europe. So, this is the amount of, or this is the average impact of one person in Europe for climate change. This is for ozone depletion and this value is for eutrophication. When you do normalize, you take the ratio of 3.56 divided by 1.12 10 to the power 4, and that gives you the normalized result by 3.17 10 to the power minus 4. So, what this tells us that for the product that we were studying, the impact is actually about 3.7 10 to the power minus 4 times of what an average person's impacted. So, it is giving you the relative value of the product impact as compared to one person impact in Europe. So, what normalization use tells us, it is helping us to compare our impact or results for that product or process with some reference value that we have selected. So, as per the results, the product being analyzed in the case where we saw the data has significantly lower impact than per person in the climate change category. And remember that the result that we showed was for the impact of product for 1 kg of product, that was the functional unit. So, what we just compared in that table is impact for use of 1 unit of that product to relative to impact per person in that impact category, and that is our reference frame. So, now the question is that is it okay to do such comparisons for choosing the product's environmental performance? And I'll encourage you to think about this question, and we will see a quick calculation to actually address this using some data. So, instead of, in our previous slide, what we did was we calculated the impact for about 1 kg of product. So, that was our functional unit. Let's scale the impact assessment to 1000 kg of product instead of 1 kg, and we will just use the linear scaling. So, now in this data, what I have done is that instead, so now these are elementary flows for 1000 times product used, and so let's say that the impact actually scales by 1000 times. So, now we have 1000 kg CO2 and our climate change impact is 1000 times now. Our methane impact is 250 and our CFC is about 2310. So, now you can see that the normalized result is telling that it is 3 times more than the person's impact. In the previous one, like we just saw, we said that the product has relatively very less impact as compared to one person in the Europe. But this result is showing it's much higher, it's about 3 times, which means that when you are doing normalization, your reference value actually plays a significant role and your functional unit. So when you are using normalization, you need to choose the reference which is comparable to your LCA functional unit. So I would say that 1 kg product is not really representative of the consumption in whole of the Europe. So if you really want to compare it with per person in Europe, your functional unit would be the total consumption or total impact of product use in that country with average impact in that country, and that would be a much fairer comparison to actually say whether the product has a higher or a lower impact than average in the country. So the crux is in this case is that it is okay to use normalization when the intent is comparison. And when the intent is comparison, you need to be cautious of using the right reference value that is used for the normalization in that particular impact category. But it is not really okay when you are making decision about absolute value of single impact category. So because you are doing normalization, you may say that this is going to have a much higher impact, but that would not be fair to tell about the absolute value of that particular product. So in summary, we can use normalization as long as our intent is comparison and we know what is the scale of that we are using and our normalization or reference value is at the same level of what we are using. So when we are doing normalization in comparative LCA, let's say we are comparing product A and product B. So we can use the normalization to see the relative performance of one product over the other. The possible normalization references in case of comparing A and B is, one, we can use total impact of A and B combined. So in that case, our normalized result will be impact of A divided by the total impact of A and B. Similarly, impact of B divided by the total impact of A and B. And that will tell us whether A and B are performing better or worse as compared to, or what is the fraction of or what is the weighting contribution of each of that product in the total impact. We can also use the average impact of A and B, which is A plus B by 2, and that will tell us whether one product is on average better than the other or not. So that is another possible normalization reference frame or reference value that you can choose if you are choosing to use normalization for comparison of two products. There is other possibility where you can just use one or the other as reference. So for example, if you use A as your reference, then the impact of A is 1 in all categories because your denominator will be the impact of A, and then you will be calculating the impact of B relative to the impact of A. So if it is greater than 1, then B has higher impact. If it is lesser than 1, then B has lower impact. And that is how we can compare whether B or A is performing better or worse than the other product when we are choosing normalization. The next non-mandatory steps in life cycle impact assessment is weighting. The weighting step is about assigning relative importance to one impact over other. And what is done? So for example, when we looked at the midpoint categories, there are a lot of different midpoint categories and you want to actually weight them by choosing some weighting factors. So the relative weights of different impact categories are expressed by the weighting factor. So you can do that at midpoint category or also at point damage category, and generally it is done at endpoint. And the idea is that you want to give a single number to the environmental impact of your product so that decision making is easier. So the main idea is that we are further reducing the dimensionality of your impact category by weighting different impact categories and adding them together. So that is what the weighting is. So here the main question is that how do we get the weighting factor? Because in characterization factors we saw that it is based on the characterization model, which is based on some basic fundamental science of how the pollutant is behaving in terms of that impact that it is creating. Here we are just doing the weighting, so we want to know how to do that weighting factor. So to do that, we will quickly do activity. So here we have 5 impact categories: climate change, water quality, species loss, human health damage and soil degradation. And I am going to ask you to weight these impact categories in order of their importance for your decision making. So take 30 seconds and just write 1 to 5 for these impact category. And of course, you will have multiple questions that come to your mind when you are doing that, but let's just take a shot at ranking them. Alright, let's look at the rankings. So this is the ranking that I have given to these impact categories. So for me, climate change is ranked 1, water quality is ranked 3, species loss is at the 5th, human health damage 2 and soil degradation 4. And I am sure if you compare these ranking to your ranking, it will not match. And the idea is that because there is no formal scientific basis of weighting or getting these weighting factor. So let's see, are there systematic ways of getting these weighting factors? So there are some weighting methods which we use generally to get the weighting factors. Of these, there are 5 that are generally used. Of course, none of them is preferable over other, and it's all subjective to the analyst on what they want to use. Monetarization, authorized targets, authoritative targets, proxies and technology abatement. So let's look one by one what these weighting factors mean. Weighting method, monetarization. This method is based in the economics of the damage or impact that we are looking. So here we use the cost of environmental damage or cost of environmental resources that is used to come up with scaling numbers. The cost of damage can be calculated as what we call as willingness to pay, such as how much are you willing to pay for avoiding extinction of species per year, or how much are you willing to pay for clean water, how much are you willing to pay for reduction in air pollution that impacts climate change. So based on that cost that we collect from market or from the users, we can then say this particular impact has a higher weighting factor than the other because the users or the people who are actually getting affected by that impact are willing to pay more. It could be the businesses, it could be the normal citizens, or it could be the government and whatever. But here the basis is the economic cost that we are putting that value on that particular impact that is used to actually weight the different impact categories. The next one is authorized targets. Authorized targets at certain levels or limits that the government or the policy makers would have put on that particular impact categories. And the way we put weight is by calculating the difference between current level of pollutants to the targeted values that can be used to drive weighting factors. So for example, if a pollutant that is higher than a target value, let's say the target value is some parts per million, and you have, let's say, 10 parts per million, that's a random number, and your impact category is at 20 parts per million. So you have definitely a higher weight because you have that difference from the target value which is authorized to be actually released in the environment, but you are releasing much higher. So it will result in higher weighting factor for that damage category. So for each of the impact category or damage category, you can identify what is the authorized level that is given by some controlling body or the regulatory body, and then what is actual impact that you have calculated, and that difference can be used to drive the weighting factor. So here is an example of weighting factor where you are actually using the ratio. So here we are saying that let's assume that the government has only authorized 0.2 kg CO2 per kg of product and 1.10 to the power 8 minus 8 kg nitrate per kg of product. So this is our authorized limit that is given by the government that is allowable. But our actual values that we get from our life cycle inventory after we do our LCA calculation is 1.94 kg CO2 per kg of product and 2.91 10 to the power minus 8 kg nitrate per kg product. So here we are going to use ratio instead of the difference, and if we look at the difference, our released value is actually 10 times higher in the climate change category, and it is about 3 points higher in terms of eutrophication, because nitrate is related to eutrophication. So if I had the climate change and eutrophication impact category, then I would rank this as 1 and this as 2, because the offshoot or the overshoot as compared to from the authorized target is much higher in the climate change category than the eutrophication category. So that is another way of calculating weighting factor if you have multiple impact categories. Other way is authority panels. Authoritative panels are mainly people who are subject matter experts, like scientific experts, government representative and decision makers, and here they can all bring in their ideas, and like when you did that thought activity, you had ranked a different ranking for different impact categories, and I had different weighting factors. So we all can pool in that analysis, share our information and actually reconcile those differences using some analytical techniques like analytical hierarchy process. We will not go into detail of what AHP entails, but AHP is a very systematic method of bringing together various stakeholders and calculating quantitatively, coming to a consensus for ranking different alternatives. So however, what happens is that in that, because the subject matter experts may bring in their information, but it's not really a quantitative way of ranking. So it's mostly subjective, and that's why we say that it's an art and science of balancing, because you are bringing multiple stakeholders and then bringing their information together to come up with quantitative numbers. In all the methods, I think this is the least preferred. However, since there are a lot of stakeholders that are involved in making decisions, sometimes a lot of companies would actually prefer this, so that they have heard all the different perspectives from different subject matter experts for ranking the impact categories. The next one is weighting method, is the technology abatement, and this is more grounded in technology, or where what engineers would prefer. So here the idea is that anything that has a technology available to reduce the impact can be used to assign weights. So for example, if there is a polluted water, we know that there is a lot of recycling technologies, ion absorption, ion exchange and all of that, that is available to actually treat the water. Hence, the impact category will be ranked lower, because we have that technological optimism that we can actually solve this problem based on the current information or the current technology available to us. But if you talk about metal depletion, we will rank that higher, because we do not have technology to actually make fresh metals out of nowhere. So that is something that is going to drive the ranking of the impact category based on whether we have abatement technologies or substitution available for that particular impact category. And that is another information that we can use for weighting different impact category based on where we have the solutions readily available and where we do not have the technological solutions readily available. So in summary, there are two non-mandatory steps in LCIA. First is normalization, which is used to compare across categories based on chosen reference. The word of caution here is to use the right reference value based on what the goal of your analysis is. It has to be comparable to the size of your product or the size of your impact that you are going to use. So you are going to use the total consumption of the product in the country versus average impact or consumption in the country, rather than 1 kg product with average product. That does not really give you a good sense of the impact. Then weighting is generally subjective, but there are really methods that can be used for weighting, such as monetarization, and then there are authoritative targets and technology abatement, etc. So you can use one of those by understanding what information you have at hand, and then decisions can be made more judiciously based on the actual impact assessed in region. And the idea is that most of the times ISO does not mandate that, but there may be LCA reports that will actually show you weighted results. In case you see any of the weighting or normalized, make sure that you understand how the weighting has been done and how the normalization has been done to be able to interpret the results more accurately. In summary, we have 5 main steps in life cycle impact assessment. We already have seen in past modules with the impact category selection, classification and characterization, which is the mandatory step. So if you have to do LCIA, those are the must do steps. And then there are further optional like normalization and weighting, which you can do based on the requirement of your analysis or the data available or information available at hand. So that finishes the third step of life cycle assessment, which is the life cycle impact assessment. We will now move forward to the last step, which is the interpretation phase, and we will just see some of the methods that are going to be used for interpretations of LCA results. Alright, so the next stage is our interpretation result. Interpretation of results is mainly the analysis of results for decision making, and we will see what kind of analysis we are going to do by looking at the LCA results. The main question in this step is how do we interpret and make use of the results from LCA models for decision making. There are few types of analysis for results of LCA. First is the analytical analysis, which includes 4 different types of analysis you can do, which is dominance analysis, contribution analysis, break-even analysis and decision maker analysis. And then the next is our testing the robustness, which has uncertainty analysis, sensitivity analysis and variation analysis. First is the analytical dominance analysis. So what is dominance analysis? Dominance analysis is mainly used to investigate what parts of the life cycle give rise to the greatest or the dominant environmental impact. So here you look at the aggregate data at different life cycle stages, and what you can infer from the dominance analysis is to identify the life cycle stages where improvements need to be made, because you will be able to identify which is the dominant life cycle stage in contributing to a particular impact that you are looking at. So that is what we call as dominance analysis, and this is very routinely done to understand which parts of your life cycle stages are actually contributing more and can be targeted for improvement. Next is the contribution analysis, which is very similar to dominance analysis, but instead of looking at the stage of life cycle, we are looking at which environmental load instead of the life cycle activity contribute most to the total environmental impact. So here the question is now different. Here instead of looking at which life cycle stage, we are looking at which environmental impact or environmental load is actually contributing the most, and that environmental load can be spread around into multiple life cycle stages. So here now what your effort will be in improving in not just a single life cycle stage, but across different life cycle stage, targeting that particular emission. And one example of that is climate change. So we are looking at CO2 reduction. So we are not focusing on one life cycle stage, but we are cutting CO2 emissions across different life cycle stages, because that is the most contribution to the climate change that we have seen so far. Then we have what we call as the break-even analysis. In the break-even analysis, it's mainly seen when you want to study the trade-offs for single-use products versus multiple-use products. So here what we are seeing is a graph that shows the orange one is showing energy in the energy used for paper making, which is in megajoules, and then energy in steel. So you can see that at this point you have crossover, which means that here both of the number of usage of your steel will actually become similar to the number of for the paper. And here we are saying that the product is now break even, which means that if you have used your steel cup this many times, then you are actually performing better than the paper cup, otherwise you are performing worse than the paper cup because you are using more energy in making the steel. So break-even analysis is basically telling at what point your multiple usage product is performing better, because after that it is actually improving in terms of energy consumption per usage. The last one is our analytical decision making analysis. Here it is mostly about understanding who controls what part of your life cycle stages, because when you do an LCA you have different life cycle stages that are being controlled by different stakeholders. So this is mostly done when you have a product life cycle with multiple stakeholders. For example, in the life cycle stage of manufacturing steel cup, we have lot of different inputs. We have raw steel input, so steel company is providing it. Energy input is provided by the power company. We have transportation support. We have water for the plant, which is provided by the public utility. Labor, facilities. You have infrastructure such as lathe machines, molding tools, finishing tools. You also have some semiconductors and maybe plastic for molding. So you can see that there are multiple stakeholders, and in this decision maker analysis, what you would do is actually break down your result into understanding who controls what part of the impact category. So even in one life cycle stages, you might want to actually break down by reference flows contributing to specific impacts, and that means that if you want to focus on reducing that impact, you know that perhaps for the CO2 emission we have these three stakeholders that are actually contributing the most, and these are the people who need to make decision to actually reduce the CO2 emissions related to those inputs. Hence, in a decision maker analysis, we are going flow by flow and actually relating it to which part of the life cycle stage is contributed or controlled by which stakeholder in that particular system, and that is what is decision maker analysis. As you can imagine, this is going to be a much challenging work because you need information about different suppliers and the inputs, and there is going to be a much greater transparency needed about the origins of different inputs that you are taking in one life cycle stage. So here, who makes the call for what is important is necessary. So the closest processes to the product are being studied, and then we identify for those which the main product company has the direct control, and where you can have more control to make changes. And the things that you do not have more control to make changes, you would need to work with the stakeholder to actually make changes. This is where actually a lot of companies and products management is actually struggling to identify how to really make their suppliers or the second order and third order suppliers change their practices so that the life cycle impact of their product can be reduced. And most of the time those alternative options of lower impact is not even available in the market. So this is a very crucial analysis when we go into the designing of the redesigning of the product life cycle so that we can reduce the impact. So in terms of the next analysis, we have robustness. So after we do analysis, we also want to test how robust are our results, and for that we do what we call as uncertainty, sensitivity and variation analysis. So what is uncertainty analysis? We have three things. We have input certainties, then we process the uncertainties, and then we have output certainties. When we talk about uncertainty, in normal language we say that we are not sure. In statistical knowledge, that's the standard error. Whenever you are measuring something, you might not know the accurate value of that, and you might have some deviation in the measurement. That is what we call as uncertainty. And in the statistical knowledge or statistical terminology, we call it standard deviation. In the LCA terminology, uncertainty can have multiple meanings. It can be incomplete information. You do not have the complete information about the life cycle stage. You can have conflicting information. You might have two different measurements for the same flow. You may have linguistic imprecision. You really don't know which flow you are talking about, and then variability, which is the standard deviation, and errors that we talk about. So we can have lot of sources of uncertainties, and the idea is that we collect that sources of uncertainty as input uncertainty in our model. We process it and we see how uncertain our output results are. So when we want to handle uncertainty in the LCA results, we identify the significant uncertainty component, which we call as a scanning uncertainty. Then we assign a standard uncertainty to each component. It can be that you have some measured value or you have multiple measured value and you want to assign a standard deviation to each of that reference flow. So that is what we call as assigning a standard input uncertainty. Then you combine, which is mainly that if you are adding or you are multiplying, there are different ways of propagating those errors, and that is more reference to the statistics behind that uncertainty propagation. But you combine that and then you calculate the expanded uncertainty and as output uncertainty. So those are the steps we follow to actually quantify the uncertainty in our LCA result. When we want to test, are we really precisely telling the impact or we are making some errors in telling that impact. Other robustness measure as sensitivity. Sensitivity is very widely used. It's mostly used in a lot of modeling paradigm where if you have a critical data or let's say a control variable or a variable that is very significant for your decision making, then you change and you see how results change. For example, if you have energy data as one input in your LCA and it is critical for your study, then you can change the value of energy, or you can change the type of energy input and you recalculate your LCA result to see how your impact category results are changing, and that will tell how sensitive is your LCA result to that particular input. If it is not that sensitive, if your total impact is still around the same ballpark number, then you say that, well, my LCA results are not really sensitive to energy input change. So it might be something else which might be controlling. So you can then do sensitivity analysis for everything. So it might not be the energy input, it might be the chemical input. So maybe you are sourcing two different chemicals and you then source it differently, or you use, instead of sodium hydroxide, you start using potassium hydroxide, and you see that the results significantly change, which means that your LCA result is not robust, it is sensitive to the input of that chemical. So we can test the robustness of your LCA result by saying, by changing one critical value parameter and then seeing how the LCA results are changing. And that's a very typical exercise that a lot of LCA analysts would do after they have done their LCA and they see that there is a particular input that might have a significant hold on the impact of your LCA result. They would test the sensitivity of your result. So that's a straightforward analysis that you can do to test the robustness of your LCA result. The next is variation analysis, and this is different than sensitivity. Here, instead of one flow, you are changing the life cycle model itself. For example, we can change the source of energy. Instead of coal, we are using renewable energy, and you can recalculate the LCA result to see how the variation of energy type is changing. You can also change the technology. So instead of, let's say, EV, we are using gasoline vehicles, and so that is what we call as variation, because we are changing the life cycle model itself by changing the scope. We are changing the different variation of that technology in our system. So it's not just changing the value of a particular input, but it's also changing the whole model behind that input in your system. So that is what we call as variation analysis. So in short, these are the different steps. So for interpretation, when we go to the process LCA example, we will see some of these interpretations, dominance and contribution analysis. We will also check for sensitivity and all of that. But in summary, in life cycle assessment, I hope so far you have learned all the steps in depth. We'll see an example through a software, and that will help you put all of this in practice. We start with the goal and scope, which defines the objective. Then we go for the inventory that is collecting all the data. We convert that inventory into impact categories so that we can reduce the dimensionality for decision making, which is the life cycle impact assessment, and then we can do all the analysis or interpretation for decision making. With that, this is the end of all the LCA steps. We will move forward with an example to show process LCA in an open source software called OpenLCA, and then further we will learn about expanding system boundaries.